Hello children, in this session I am going to continue with the topics of electric field. On the last session also we discussed some of the important topics of electric field. I think we can have a very quick recap. What are the topics we studied? We started from the definition of electric field intensity. So what about the formula we got is E vector is limit Q naught tends to 0 F vector by Q naught. So obviously it is a ratio of force and charge. Secondly, we studied an expression for electric field due to a point charge. What about the expression for electric field due to a point charge? It was kq by r square. Later, we get into the concept of electric lines of force. We studied the properties of electric lines of force. We represented different lines of force for different types of charges. And we get into electric dipole. We studied the application of electric dipole where we focused on two cases, that is electric field on the axial line and electric field on the equatorial line. So I am going to continue with the concept of electric field. Today I am going to focus on the topic of torque acting on a dipole. We are going to derive an expression for torque acting on a dipole. So let us consider, I am going to start with a uniform electric field. I'm going to consider a uniform electric field. A uniform electric field is represented by parallel arrows as shown with same direction. So obviously this is the representation of uniform electric field. In this electric field, I am going to keep a dipole. So you know what is a dipole? Dipole, the two ends of the dipole are AB. They are having charges minus Q and plus Q. What about the length of the dipole is 2A. The length of the dipole is 2A. Let the dipole is placed making an angle theta. Let the dipole is placed making an angle theta with the direction of electric field. Once again, I am going to explain. We considered a uniform electric field, E vector. In this electric field, we placed an electric dipole AB with charges minus Q and plus Q with a separation 2A. The dipole is kept at an angle theta with the electric field. Now, before getting into the content, I am going to speak, if this is an electric field due to some source charge, in this electric field, if I am going to place a charge, what happens to the charge? The charge experiences a force, that is F vector is equal to QE vector, and this is one of the important formula I am going to use in this concept. Once again, if a charge Q is placed in a uniform electric field, it experiences a force. What is the forces? F is QE. I think how the formula you got is, you know, E was F by Q. From this, I am getting F is equal to QE. Now, what happens to the charge minus Q at A? You know, by the same concept, I am going to write. It experiences a force, say F vector is equal to minus QE vector. Similarly, what about the force on plus Q at B? It will also experience a force, F vector is equal to plus QE vector. Once again, minus Q experiences minus QE vector, whereas plus Q experiences plus QE vector. Now you say the dipole is under the action of two equal, unlike and parallel forces. Once again, the dipole is under the action of two equal, unlike parallel forces, and you know, if two unlike parallel forces acts, what happens to the dipole? The dipole experiences a torque. The dipole experiences a torque. This means the dipole starts rotating in the electric field. Once again, what about the force on minus Q at A is minus QE? What about the force on plus Q at B is plus QE? The dipole is under the action of two equal, unlike and parallel forces, and ultimately what happens to the dipole? The dipole experiences a torque. Now, I am going to derive an expression for torque. You know, what about the expression for torque? I can start. you know torque is denoted by tau, is either force into perpendicular distance between the line of action of force. What is the formula for torque? Is either force into perpendicular distance between the line of action of force from the axis of rotation. I think from 11th you know what is the concept of torque. Once again, torque is the product of either force and the perpendicular distance of line of action of force from the axis of rotation. Now either force means since the two forces are equal in magnitude, I can take any force. So I am going to mark it as F can be written as QE into, what about the perpendicular distance? Once again, AB is not the perpendicular distance. So to get the perpendicular distance, I am going to do a construction like this. Then I am going to mark this as N. Then AN represents the perpendicular distance. AN represents the perpendicular distance. Now, geometrically, if this is theta, I can mark this angle is also theta, and obviously this will be 90 degree. I can apply the concept of trigonometry, that is, what is sine theta from that right triangle? So what is sine theta from that right triangle is, sine theta is AN by 2A. AN by 2A. So what about AN will be 2A sine theta. So I can put it here. So what is tau is equal to QE into 2A sine theta. You know what is Q into 2A is electric dipole moment, that is P E sine theta. Now this is the magnitude form of torque acting on the dipole. Now how to write in vector notation? So it will be tau vector is equal to P vector cross E vector. That is the vector form of torque experienced by the dipole. Once again, what is the formula for torque is either force into perpendicular distance. Either force, I am writing it as QE. What is the perpendicular distance? It is obtained from construction, that is AN represents the perpendicular distance between the line of action of force. So from trigonometry, that is I am using sine theta is AN by 2A. From the right triangle ANB, what is sine theta is AN by 2A, that is length of the dipole. This implies as AN is equal to 2A sine theta. Put it back, tau comes to be PE sine theta, and in vector form it is P cross E. Now I am going to discuss the conclusions of this expression. What are the important conclusions that we can draw from this expression? The very first, when a dipole is placed in a uniform electric field, it experiences only a torque. What I am saying is, when a dipole is placed in a uniform electric field, it experiences only a torque. The net force on the dipole is 0. Once again, it's a very important conclusion. The dipole only experiences a torque, whereas the net force, you are able to see minus QE and plus QE, the net force on the dipole is 0. Second, what about the value of torque? Yeah, when I can say the value of torque is minimum. You know, if the dipole is aligned along the direction of electric field, if the dipole is aligned along the direction of electric field, this orientation leads to 0 torque. Once again, what about the orientation which leads to minimum torque? When the dipole is aligned along the direction of electric field, that represents minimum torque, and that is also the condition for stable equilibrium. Once again, in 1 mark question, in board questions it is asked, what orientation of dipole corresponds to stable equilibrium? So you are going to write the orientation, that means when P vector parallel E vector. This means the dipole moment is parallel to the electric field. This orientation corresponds to stable equilibrium, and also the torque here is minimum. Now, the next one, when the torque value will be maximum, or I can say when the dipole experiences maximum torque. Ultimately, when the dipole is kept perpendicular or at right angles to the direction of electric field, it experiences maximum torque. So these are some important conclusions related to torque acting on a dipole. Now, I am going to get into the concept of area vector. Yes. Yes. We know area is basically a scalar quantity. Area is basically a scalar quantity, but in some situation or in some problems, we are supposed to represent area as a vector. Once again, area is basically a scalar quantity, but in some situation or problems, we are going to assume area as a vector. Now, we can assume a very simple example. What is the need for associating a vector with a area? Let us suppose that I am holding a ring in a stream of water. I am holding a ring in a stream of water, and my aim is to get what is the amount of water flowing through the ring. My aim is to calculate or determine the amount of water flowing through the ring. Now, naturally we know the amount of water flowing through the ring depends on the way in which we are holding the ring. Once again, I am repeating the same thing. Once again, my aim is to find the amount of water flowing through the ring. So, the amount of water will depend upon how I am holding the ring. So, let us suppose that if I am holding the ring normal to the flow of water, obviously the flow or the amount will be maximum. If I am going to hold the ring parallel to the flow, the amount of water flowing will be minimum. So ultimately, orientation to the surface is a must in such cases, and that is the need for area to be treated as a vector. Now, how to give some direction to a closed surface? Now the question comes, how we can give some direction to a closed surface? For that, let us suppose that I am going to assume this is a closed area. This is a closed area. So in order to give some direction to a closed area, I am going to divide this larger area into a large number of very small area elements. I am going to introduce a new word, area element. Once again, what do you mean by area element? Obviously, it is a segment of that larger area. So I am going to assume this is one such smaller segment. This is one such smaller segment, and I am going to mark it as ds. Going to mark it as ds. So what about ds? ds can also be termed as a planar. ds can also be termed as a planar. As we know, normal to the plane specifies the orientation of the plane. Once again, I am going to repeat. If I am going to say normal to a plane, what a normal to a plane specifies or represents? It specifies the orientation of the plane. So what about the direction of a planar area vector will be along its normal? I think the concept is little bit typical. I am going to explain once again. In order to give a direction to a closed surface, I am going to assume a larger area. I am going to assume this larger area is consisting of large number of very small area elements. One such element I am going to mark it as ds. This area element can be termed as a planar. What I am saying about planar? As normal to the plane specifies the orientation of the plane. So I can say the direction of a planar area vector will be along its normal. Now, you know, normal can be drawn in two directions. It can be normal inwards. It can be normal outwards. So by convention, if I am going to give direction to an area element for a closed surface, I will be drawing outward normal. What is the word I am going to use is, I am going to draw outward normal like this. So I am going to mark, this is unit vector n cap. So n cap ds represents the area element vector, that is ds vector. Once again, it is the most important concept that will be very useful for studying of the next topic, that is Gauss's theorem. Yes. Now, I am going to get into the next topic, that is electric flux. Electric flux. Flux, we know, flux means flow. Electric flux means it is the flow of electric lines of force through an area. It's a very simple language I am going to speak. Electric flux is the total number of electric lines of force crossing through an area. But I am going to use a word, how the flow is normal to the surface. Always, whenever I am going to speak the word flux, The flux will always be normal to the surface. I think this normal word will be very clear when I am going to get into the derivation concept. So once again, what is electric flux? I can say electric flux linked with the surface, where the surface is held. Let the surface is held in an electric field. Then how I can define electric flux? It is the total number of electric lines of force crossing in a direction normal to the surface. Crossing in a direction normal to the surface. Now, what is the symbol for electric flux? Basically, it is denoted by phi. It is denoted by phi. Now, I am going to establish a relationship between electric intensity and electric flux. So, what about the relation for this? I am going to assume a uniform electric field. I am going to assume a uniform electric field. Already you know how to represent a uniform electric field. Say this is uniform electric field E vector. In this, I am going to assume a closed surface of area S. I am going to assume a closed surface of area S. Now my aim is to find the flux through this entire surface. My aim is to find the flux through the entire surface. So for this, I am going to assume a very small area element. I am going to assume a very small area element. I am going to mark it as ds. I am going to mark it as ds. Now, what about normal to ds? You know, that will be the area element vector. Let us suppose that the area element vector, that is ds vector, makes an angle theta with the direction of electric field. I am assuming this. Whereabout you know how to draw the area vector. Obviously, it will be normal to the planar. It will be normal to the planar. So ds is the small element, whereas ds vector is the area vector. Where it acts outward normal. It acts outward normal. And let us suppose that area element vector makes an angle theta with the direction of electric field. Now you say, what about the component of electric field along normal? I can mark it as En is equal to E cos theta. I think this will be very clear. Once again, whenever I am going to speak about flux is something related to normal. So I am going to concern with the flow along the normal direction. So you can assume, what about the electric field normal to the element or along ds vector will be En is equal to E cos theta. Now I can get what is the small flux. Obviously it is a small elemental area. So what about the small flux flowing through this small elemental area ds can be written as En ds. So what about En? I am having En as E cos theta ds, and you know obviously cos theta comes from dot product. So it can be written as E vector dot ds vector, that is d phi is equal to E vector dot ds vector. Once again, I am going to explain this most important content. In order to establish a relationship between electric flux and electric field intensity, I am assuming a uniform electric field E vector. In this uniform electric field, I am going to keep a surface of area S. My aim is to find what about the total flux that is linked with the entire surface. For this, I am going to assume a very small area element ds. Now I am drawing ds vector. Obviously it is area element vector. It is always drawn outward normal. So this ds vector is drawn outward normal. Let that area vector makes an angle theta with the electric field. So obviously, which component of electric field is responsible for flux is E cos theta. Now I am going to get what is the small flux linked with the small elemental area, that is d phi is equal to En into ds. En is E cos theta ds, and finally I am getting d phi is equal to E vector dot ds vector. Obviously this is the small flux linked with the small area element. So what about the total flux? I am going to mark like this. It will be the entire surface integration over the closed loop of that value, E vector dot ds vector, and this becomes the expression for the total flux linked with the entire surface area. What do you mean by this? It is integral, that is surface integral. What do you mean by this circle? Over the closed loop dot product of E vector and ds vector. Our next topic is Gauss theorem. We studied the concept of area vector we studied the concept of electric flux only to understand what is Gauss theorem. So as it is a theorem, obviously it has a statement. So what Gauss states, I am going to explain. What is the electric flux? You know, electric flux is denoted by, for a closed surface, it is denoted by this symbol. If it is an open surface, I am going to use this symbol. So Gauss theorem is applicable only for closed surfaces. So what about the total electric flux linked with a closed surface? I am going to assume this is a closed surface in which Q charge is enclosed. So what, according to Gauss theorem, the total electric flux linked with a surface enclosing a charge Q is equal to 1 by epsilon naught times the magnitude of charge enclosed. This is the statement of Gauss theorem. What is Gauss theorem once again? Gauss theorem states that the total electric flux linked with a surface enclosing a charge Q is equal to 1 by epsilon naught times the magnitude of charge enclosed. And this is the statement of Gauss theorem. So Gauss theorem speaks about the flux linked with the surface. So the flux depends on the charge. Now, you know already we derived an expression for phi. It will be closed loop surface integral E vector dot ds vector is equal to Q by epsilon naught. This is the second form of Gauss theorem. So obviously both the things are same, but it is the second form of Gauss theorem. So what Gauss theorem states? The total flux linked with a surface enclosing a charge Q is equal to 1 by epsilon naught times the magnitude of charge enclosed. Now I am going to prove this. So to prove this, I am going to assume a sphere. Say O is the center. At the center, I am going to keep a unit positive charge, say plus Q. I am going to assume a point P on the surface where E is the electric field due to this charge on the same line. Once again, I am going to consider a sphere. What about the center of the sphere is O? At the origin, I am going to keep a charge plus Q. Next, I am going to assume a point P, say which is at a distance R from the center where E is the electric field. So what about the expression for electric field due to this point charge? Already we derived on the last classes. E vector is equal to 1 by 4 pi epsilon naught Q by R square R cap. Mark it as equation number 1. I am writing in vector form. Now, you say our aim is to find what is the flux linked with the sphere. So once again, I am going to assume a small area element around P. I am going to assume a very small area element around P. Let that area element vector, ds vector, also acts along E vector. That area element vector, ds vector, also acts along E vector. Now this means E vector and ds vector are parallel. Now you say, what is the expression for small flux linked with the small area? Already we have a small formula. d phi is equal to E vector dot ds vector. Yes, mark it as equation number 2. I can use 1 and 2. So what will happen, you say? So d phi is equal to 1 by 4 pi epsilon naught Q by R square R cap dot ds vector. Now remove the dot. d phi is equal to 1 by 4 pi epsilon naught Q by R square. Unit vector has a magnitude 1. Remove dot ds. So obviously it will be ds cos theta. Theta is the angle between E and ds. Since they are acting parallel, theta can be written as 0. So obviously I can eliminate that. So d phi is equal to 1 by 4 pi epsilon naught Q by R square ds. Why? Since you know E vector parallel ds vector. Yes, mark it as equation number 3. Now, since I am going to speak, this is the small flux linked with the small area element. Our aim is to get the total flux with the entire sphere. So I am going to get the total flux, that is, say if phi is the total flux, I am going to integrate it over the entire surface, that is 1 by 4 pi epsilon naught Q by R square ds. All the things are constant except ds. So 1 by 4 pi epsilon naught q by r square surface integral ds. What is surface area of a sphere is 4 pi r square. So I can put it. So what I'm going to get is 1 by 4 pi epsilon naught q by r square into 4 pi r square. This means this entire thing is replaced by 4 pi r square. R square cancels off, 4 pi cancels off. So what is the thing that is left is q by epsilon naught. So I started from phi and I am ending at q by epsilon naught, and you know that is our Gauss theorem. That is, Gauss theorem is phi is equal to q by epsilon naught, and this is the proof of Gauss theorem. Once again I am going to speak. In order to prove Gauss theorem, we considered a sphere with center O, radius r. Let a positive charge plus q is placed at the center of the sphere, number 1. Number 2, I am going to consider a point P on the surface of the sphere where the electric field intensity is given by E is equal to 1 by 4 pi epsilon naught q by r square r cap. I am writing the electric field intensity in vector form. Mark it as equation number 1. Now, in order to find the flux through the entire surface, already we know I am going to assume a small area element, that is, say ds, it is around P. I am going to assume the area element is around P such that the area element vector acts along E vector. Such that the area element vector acts along E vector. Now, what about the small flux linked with the small area is d phi is E vector dot ds vector. Now put equation 1 and 2. D phi is 1 by 4 pi epsilon naught q by r square r cap dot ds. Remove dot, cos theta comes. Since E and ds are parallel, theta is 0. So ultimately I am getting d phi is 1 by 4 pi epsilon naught q by r square ds. This is the small flux linked with the small area. But my aim is to get the total flux through the sphere. So I am going to integrate it. D phi becomes phi. Make a surface integration over the entire sphere. ds integral comes to be 4 pi r square. And after simplification, phi comes to be q by epsilon naught. And this is the proof of Gauss theorem. In fact, Gauss theorem can be proved for any surfaces. For simplicity, we assume to be a sphere. It can be drawn for, it can be proved for any surfaces. Now, I am going to introduce a very new term, Gaussian surface. What do you mean by a Gaussian surface? Gaussian surface, before getting into Gaussian surface, you know, we studied Coulomb's law, we studied superposition principle. Ultimately, they are all used to find the electric field intensity. They are all used to find the electric field intensity if the problems involved are simple. But if the problems are complicated, where we can't apply Coulomb's law or superposition principle, we are supposed to use Gauss law. We are supposed to use Gauss law, and in order to apply Gauss law, we are supposed to evaluate the surface integral. We are supposed to evaluate the surface integral, and to evaluate surface integral, I am going to assume some closed surfaces around the charge distribution. To evaluate surface integral, what is the need? We are supposed to choose some closed surfaces around the charge distribution. That closed surface around the charge distribution can be termed as Gaussian surface. So once again, what is Gaussian surface? Gaussian surface is basically a closed surface Gaussian surface is basically a closed surface. It may be around any type of charge distribution, but what about the condition? The electric field intensity at each point on the surface should be same. Any surface cannot be treated as a Gaussian surface. What is the condition? What is the type of surface I am going to close? At each and every point, the electric field intensity should be same. And the second condition, flux should always be normal to the surface. The flux should be always normal to the surface. That type of closed surface is termed as a Gaussian surface. That's all for today's session. I'm going to wind up with the topics. Before winding the session, let us check our learning. I'm going to put 2 questions only. What is the first question? You are supposed to show diagrammatically the orientation of the dipole. What you are going to do? You are going to represent the dipole in the field for which the torque is maximum. What is my first question is, you are going to show diagrammatically the representation of a dipole in the field for which the torque is maximum. Already you know, when the torque is maximum and the dipole is at right angles to the electric field. I am going to represent the diagram. So say if this is the electric field Say if this is the electric field, this is a uniform electric field. What about the dipole? The dipole should be kept like this. The dipole should be kept like this. So I'm going to write it as minus q plus q. And this orientation of the dipole corresponds to maximum torque. Second question, if in the same question they are asking what orientation corresponds to half the maximum value of torque. Now we know 90 degree corresponds to maximum torque. So we have a sense key 45 degree will lead to half the value, but it is not so. You have to check mathematically. You know tau is P E sin theta. They are asking maximum is tau max, and you know by putting sin 90 it comes to be P. What about they are asking half the maximum means? I am going to get PE by 2. So when to get PE by 2? If I am going to put 30 degree, then only I am going to get half the maximum torque. So what orientation? This means the dipole is kept at 30 degree with the electric field. So you can see the diagram orientation will be like this. So it will be like this. Minus q plus q, and the angle is 30 degree. This orientation corresponds to half the maximum value of torque. Now the same orientation for zero torque. You can speak. What about the zero torque orientation? Already you know. Say if this is the uniform electric field, zero torque is represented like this. That is minus q plus q. This means P vector and E vector are parallel, and also you know this is the stable equilibrium of the dipole. So this is one type of question usually asked in board. Second question I am going to ask. An electric dipole of dipole moment. What about the dipole moment? Dipole moment is given to you, that is P vector is 20 into 10 power minus 6, that is 20 into 10 power minus 6 coulomb meter. It's a dipole moment associated with an electric dipole, is enclosed by a closed surface. Obviously a dipole is enclosed by a closed surface. Say this is a closed surface. Now what is the question? What is the net flux coming out of the surface? You are supposed to get what is the net flux coming out of the surface. You know flux depends on the charge. Flux depends on the charge. And you know electric dipole has equal and opposite charges. So what about the net charge is 0? The net charge is 0. This means if there is no charge, there will be no net flux. Obviously there is a charge. Individually if I am going to speak, the dipole has charges. But what about the net charge? Is 0. Therefore the net flux through the surface will be 0. So this is one sort of important question that usually comes in the board. That's all for today's session. Thank you. Stay at home. Stay safe. Keep learning. Take care of yourself.